Hello and welcome to the European Space Agency's press briefing on the occasion of the release of the first images from Solar Orbiter. Solar Orbiter is a new sun-observing mission, a collaboration between ESA and NASA, and it was designed and built to take the closest ever images of the sun. My name is Teresa Poltarova. I am a science editor at ESA, and I will be your host today. And joining me online, mostly from their homes, because we are still in this socially distanced COVID-19 situation, are 6 amazing guests who are among the key people who made this mission possible, who brought it to life, and who will be responsible for the cutting-edge science that it's going to deliver, which will really transform our understanding of the processes on the sun and how that influences the entire solar system. My first guest is Daniel Miller, who is ESA Solar Orbiter Project Scientist. Hello, Daniel.
Hello, Teresa.
Our second guest is Holly Gilbert, who is the director of the Heliophysics Science Division at NASA Goddard Space Flight Center, and also Solar Orbiter Project Scientist at NASA. Hello, Holly.
Hello.
Our third guest is David Bergmans of the Royal Observatory of Belgium, and David is the principal investigator of the Extreme Ultraviolet Imager, or EUI, which is one of the 6 remote sensing instruments, the telescopes on Solar Orbiter. Hello, David.
Good afternoon, Teresa.
Our fourth guest is Sami Solanki, the director of the Max Planck Institute for Solar System Research in Germany, and principal investigator of the Polarimetric and Helioseismic Imager, which is another really interesting telescope that Solar Orbiter carries. Hello, Sami.
Hello, Teresa.
Next, we have Chris Owen of the University College London's Mallard Space Science Laboratory. And Chris is the principal investigator of the Solar Wind Analyzer, which is one of the 4 in situ instruments on Solar Orbiter. And these instruments don't take images, but measure the properties of the environment around the spacecraft. Hello, Chris.
Good afternoon, everyone.
And last but not least is José Luis Peón, who is Solar Orbiter Spacecraft Operations Manager at the European Space Operations Center in Darmstadt, Germany. Hello, José.
Hello, everybody.
Before we start, let me add for the journalists who are hopefully watching us right now, if you have any questions, please send them to media@esa.int. And at the end of this briefing, we will try to answer as many questions as possible. Again, the email address is media@esa.int. You can also join the conversation on Twitter using the hashtag #TheSunUpClose. Again, the hashtag is #TheSunUpClose. And let's start with the questions. Daniel, I said at the beginning, one of the tasks of Solar Orbiter is to take the closest images of the sun. The images that we are going to see today, are they already the closest images?
Yes, Teresa, indeed. We've never been closer to the sun with a camera. And this is just the beginning of the long, epic journey of Solar Orbiter, which will take us even closer to the sun in less than 2 years' time. And as far as taking high-resolution images goes, there are 2 options: getting closer to the object of interest or building a bigger telescope. That's a little bit like going on an expedition. You either get closer to the elephant or you use a bigger camera. So the world's largest solar telescope to date is the Inouye Solar Telescope on Hawaii, which has a diameter of 4 meters. But ground-based telescopes have one major drawback, and that is the fact that Earth's atmosphere is blocking large parts of the spectrum of sunlight. So if you want to observe the sun in ultraviolet light and X-rays as we want, we need to go into space. And Solar Orbiter is using what we call gravity assist maneuvers or slingshot maneuvers at the planets Venus and Earth to get closer to the sun. And we do this by harnessing the gravitational field of the planets to slow down our spacecraft and make it fall towards the sun just a little more rather than just flying around it.
Can you just tell us the images that we are going to see today? When were they taken and how far was Solar Orbiter from the sun at that moment, and how it compares to the distance from Earth and perhaps the ultimate distance of Solar Orbiter?
The images that we are going to see soon were taken around the time of our first close approach to the sun, which was at 77 million kilometers, which is just over half the distance between Sun and Earth. And so this is not quite as close as we will eventually get. Our closest approach will be just over a quarter of the distance between Sun and Earth. And we will reach that in about 2 years' time.
My next question is for Holly. Holly, Solar Orbiter, as we said, is taking the closest images of the Sun, but many people know that NASA's Parker Solar Probe is actually flying much closer to the Sun than Solar Orbiter. Can you explain to us why Parker Solar Probe is not taking images?
Indeed, Parker Solar Probe is going closer to the Sun, much closer, within 9 solar radii. But the environment that close is extremely harsh. And so they don't have many cameras. They have one camera that's not facing the Sun. It's facing away so that it can watch the solar wind. But cameras can't go that close. So Solar Orbiter is really the limit where the cameras can take images of the Sun itself.
Can you compare the environment in which Parker's Solar Probe is and that of the Solar Orbiter?
Well, if you imagine many times the Sun at the intensity, and as you get closer and closer to the Sun, Solar Orbiter isn't as close as Parker, and each time you get closer, the more intense it gets, and so the environment just gets too harsh as you get that close to the Sun.
There are many other spacecraft studying the Sun, and many of them are actually orbiting the Earth. And there are also, as Daniel already mentioned, many ground-based telescopes which provide really great resolution. What is the advantage of having a mission like Solar Orbiter in this mix, and what is the unique contribution of Solar Orbiter to solar science?
In order to understand how the Sun really creates that plasma bubble and how it modulates the environment in the solar system, we need many observations. And so we often combine observations from different observatories, including ground observatories. But Solar Orbiter in this mix offers a couple of very unique aspects. One is its orbit. It will eventually get out of the ecliptic. As it's getting closer to the Sun, it will get out of the ecliptic, which is the plane that the planets all rotate around the Sun in. So up to now, we've only been able to really image that part of the Sun from the Earth's perspective. But we're going to be able to take images and pictures of the polar regions of the Sun for the very first time. And this is extremely exciting. And also the powerful suite of instruments that Solar Orbiter offers. It's a combination of the ones that take images, the remote sensing, and the ones that are sampling the plasma, the in situ data. And so that combination really allows us to make links and connections to what's happening on the Sun and what's happening at the spacecraft.
Thank you. The Solar Orbiter mission had a very unusual start to its operations. Solar Orbiter was launched on the 10th of February this year. Less than a month later, it became clear that the new coronavirus causing the COVID-19 disease was spreading in Europe. ESA took a very early action at the time, and by mid-March, most staff members were working from home. It is no exaggeration to say that the Solar Orbiter became the first spacecraft in ESA's history that has been mostly commissioned from people's homes. Jose, my next question is for you. The early months in the orbital life of any mission are probably the most challenging. What was going through your head when the COVID-19 situation started unfolding in the middle of the commissioning?
Well, you are right. We were very worried. As you said, Solar Orbiter was launched on the 10th of February. And already towards the end of February, we were getting instructions from our management with respect to the visitors that would be allowed to enter the ESA control center in Germany, our site. So traditionally, commissioning is performed with the instrument teams together with us here in the control center. And we started to realize that if the pandemic would evolve, as it has unfortunately evolved, this would not be possible. So we worried. Travel restrictions were imposed also to the different countries where the research institutes that manage the instruments on board Solar Orbiter are located. So we had to plan another way of performing commissioning, and it was from home partially, but also on site, keeping severe restrictions.
So can you describe to us exactly how you dealt with the situation?
Well, yes, we had to stop the commissioning for almost 10 days during March. We had to replan everything. We had started the commissioning in a traditional way with the teams here, But when the lockdown came to reality, we had to replan everything. So one of the biggest restrictions was that only 2 engineers could be in the control room at the same time, keeping distance. And of course, the instrument teams were in their home countries. We had to do everything remote via teleconference, showing them what we could see in our control screens. So it was difficult, but it has worked pretty well, I think better than we expected. I think the teams are happy, we are happy, and we managed to bring the commissioning to a successful end.
That's fantastic. Thank you. Chris, I know that the work of the solar wind analyzer team was quite badly affected by the COVID-19 pandemic and the restrictions. Can you tell us how was the situation for you?
Yes, I guess like everybody else in the world, the last few months have been unexpectedly challenging. In particular, our set of sensors all use very high voltages to make their measurements, and we would normally get those turned on after waiting for several weeks after launch in order to allow all the atmospheric pockets of air that might be trapped in the instrument to get out. So actually, by the time we were ready to go and turn our instrument on, we were pretty much up against the set of lockdowns. And by the time we came out of the ESOC lockdown and were ready to go, we were also locked out of our own labs. So we've had to set up a system where doing this very delicate operation where we would go to try to ramp up to something like 30,000 volts at steps of 25 volts at a time. And at each step looking very carefully at the data coming back to make sure that nothing had gone wrong. A very delicate operation needed to be done from our home, so we had like multiple WebExes running where we had one connection to the spacecraft operator. We had another one to members of the team who were all looking at the data that Jose Luis talked about. We had a very narrow field of view from a webcam at ESOC looking at the most important parts of the data. And then trying to download the data and plot it on the fly as much as we can to make sure it was safe. But that meant that we were sending a risky command and having to wait a few minutes to see the result, which was pretty stressful. But as Jose Luis says, in the end it was good and successful. So yeah, we're happy.
Sami, how was the experience for the FIT team?
Yes. So in the beginning, things started very normally, but then the pandemic hit. And everything was shut down. Actually, the instruments, the spacecraft, they were more or less put on standby. And I was really worried at that point, because the spacecraft was just hurtling away from the Earth to speed, and we cannot continue with the commissioning and have no idea what our instrument is like. Thanks to a lot of work and the good ideas coming from the staff at ESOC, we managed to do the commissioning again, and it was challenging indeed. It was indeed quite challenging because we had to have teams, complex team in 3 countries, many different institutes, and we had to make sure that we can all communicate, up to 20 people, all doing it online instead of in one big room. But we managed to do that.
Thank you.
So finally, it worked.
Fantastic. Let's have a look at the images, because I think that's what everybody's waiting for. David, the Extreme Ultraviolet Imager, or EUI, that's one of the 6 telescopes aboard Solar Orbiter. Can you just quickly explain to us what does this instrument enable you to do?
Okay, so the thing is that Solar Orbiter will fly 4 times closer to the Sun than the Earth. And that implies that, as seen from Solar Orbiter, the solar disk will be 16 times bigger. So whenever something happens on that big solar disk in the space, EUI will be watching and imaging and monitoring all these phenomena from the smallest to the biggest scales.
How does it compare? Yeah, how does it compare to similar instruments that have been used before?
So EUI is a sort of the last in an evolution. There is always new technology coming in, but I think what the revolutionary aspect of EUI is what Daniel already said. is we're bringing it closer to the elephants. By looking from close by, we get so much sharper images. And not only will we get closer images, but we will see from a non-Earth perspective. That is, we will look down on the poles, something we've never done before.
The images that we're going to see in just a very few short moments were obtained at the end of the so-called commissioning phase, and that's the early period of technical validation. Solar Orbiter is not yet in its full science mode, so it was essentially the first opportunity to properly test all these instruments. What did you expect from those images, and when did they finally started coming? What was your impression?
To be honest, I didn't dare to expect anything. The last months of the development of EOI had been extremely stressful, with our mirrors taking apart in the last moment and re-gluing everything, and software being changed in the last minute. So it was kind of a battle to get it all together. And then when the first images came in, the first thought was, this is not possible. It cannot be that good. So it was really much better than what we perhaps not expected, but what we dared to hope for.
So hopefully now everybody should see a video clip, which is showing a sequence of videos and images from EOI. David, can you explain to us what is it that we can see in this sequence?
We see different solar instruments being displayed here. This is not EOI, but it's METIS and the solar HI instrument showing the far corona. If we can play back this video to the beginning, then we'll see EOI. No.
Anyway, let's start kind of focusing on the really interesting bit. I understand we might be having a little bit of technical problems. When we see the detailed images of the sun's surface, there is something really interesting that caught your eye when you first saw them. Could you explain this a little bit? What's that we can see there, and why is it interesting?
Right. So the very first high-resolution images that we took were not pointing anywhere specifically. We are seeing a small disk, part of the solar disk here, of the corona, which we essentially call the quiet corona. Quiet meaning that nothing is supposed to happen here. But then when you look at it at high resolution, it's amazing in the smallest details how much stuff is going on there. We couldn't believe this when we first saw this. And we started giving it crazy names like campfires and dark fibrils and ghosts and whatever we saw. So there is so much new small phenomena going on the smaller scale that we are like starting a new vocabulary to give it all names. And many of those things have been seen before at bigger scales, but never at this small scales in the quiet corona.
Thank you. Daniel, what do solar scientists know about these little campfires, these little phenomena, and how much has been known, how much have they been observed before?
Well, Teresa, like David was saying, to our knowledge, many of these particular features have not been observed before at this scale. These are clearly just the first test images, so it's too early to draw any scientific conclusions. But our conjecture is that these campfires and ghosts are related to changes in the sun's magnetic field, a process that is known as magnetic reconnection. So we believe that even though it's the quiet sun and there are only very small scale magnetic fields, these field lines do get tangled and get under stress. And like rubber bands, they can eventually tear and then reconfigure into new configurations. And that tearing process can release energy, vast quantities, and that would then heat the plasma locally to temperatures of more than 1 million degrees, which is what we see in any case in the EOI images.
I understand that these campfires could be involved in one big solar science mystery, and that is the heating of the corona. Can you explain what that is? Why is it a mystery, and how these campfires could be connected to that?
The fact that the sun's corona is so hot has really been a mystery for many, many years. It's a little counterintuitive because you would think if you have a body that's very hot at the center and relatively cool at the surface, it would be even cooler the further you go away. But on the contrary, for the sun, we have a hot core, a relatively cool surface of just about 5,500 degrees, surrounded by a super hot atmosphere of more than 1 million degrees. It's as if you would light a fire, and as you move further away from the fire, it doesn't get cooler, but in fact, it really starts to burn you when you're really far away. So that is really the peculiar thing about the sun's corona and the corona of other stars as well. There have been multiple theories put forward to account for that, including shock waves and other phenomena. Most of them, although, are related to changes in the sun's magnetic field. And there's a theory put forward by a great US physicist, Eugene Parker, after whom the NASA Parker Solar Probe has been named, who conjectured that if you should have a vast number of tiny flares, so similar to the flares that we have observed on bigger scales, but just a lot smaller, all the time in the sun, that might account for an omnipresent heating mechanism that could make the corona hot. So while we clearly do not know yet if what we see is in any way related to that theory, there is a possibility that what we see here are, let's say, the tiny cousins of the solar flares that we already know, and they produce heat on a very different scale, but because of their multitude, they could contribute significantly to heating the solar corona.
Thank you very much. Holly, the images that we are seeing here just now, there, as we said, only the first images. Seeing them, what does it suggest about the future potential of the Solar Orbiter mission?
Yeah, I think most importantly, it demonstrates that we are going to be able to accomplish our solar objectives of Solar Orbiter. We are very excited that everything is working. And it also confirms the importance of looking at different physical scales. If we've already made some discoveries in just the first light images, just imagine what we're going to find when we get closer to the sun and when we get out of the ecliptic. Very exciting.
We mentioned before that one of the goals is to look at the poles. So what do you hope to see there on the poles, and what do you think to learn from Solar Orbiter images of the poles?
Well, we don't know what we'll see yet, and it's very difficult to get out of the ecliptic because it takes a lot of energy. And so by imaging the poles, we're looking forward to seeing the magnetic field and the different flows there. And that's really important for understanding the global magnetic field of the sun. Those polar regions are important. And so we'll be able to model better the global magnetic field, how it's interacting with itself, and how it's driving space weather. So it's going to be really, really exciting to see what those poles offer and determine a little bit more understanding about how the sun operates and how it drives its heliosphere.
Thank you. Sami, let's have a look at Phi. Can you explain to us what does Phi enable you to do and why is it unique?
Yes, gladly. So Phi is a magnetograph. That means it is an instrument which measures the magnetic field of the sun close to its surface. At the same time, it also measures velocities close to the surface of the sun, which include the oscillations. The sun as a whole is oscillating all the time. And with these, we can peer into the sun, look at the interior. It's unique in the sense that, first of all, no magnetograph has ever been as close to the sun as Phi has, and that has its advantages, obviously. Secondly, it's the first magnetograph that's going to look, or is now already looking at the sun from a different direction than you can from the Earth. And so we are also seeing parts of the sun which are otherwise not visible. And finally, Phi is unique because it will be the first instrument to look at the sun from outside the ecliptic, and that's where it will really come into its own.
We are now at the so-called solar minimum. The sun is very quiet. What does it mean for the images that you are able to obtain?
Yes, so the quiet sun means that it has very little magnetic field compared to what it will hopefully have in a few years' time. That means that this magnetic field is also sort of randomly distributed over most of the sun in small features. The images sort of look bland, not very exciting, but that will change as the sun becomes more active.
I understand that in spite of that, you were able to have some interesting first. Can you tell us about this?
Yes, as I said, Phi is the first instrument or the first magnetograph to look at the sun from the side, so to say. We still haven't reached the far side of the sun, but at least from the side. And we have seen in our full disk magnetograms an active region which is totally invisible from the Earth. And that's exciting because we know that the magnetic field is a kind of holistic feature of the sun. It threads through the atmosphere and connects very different parts of the sun with each other. But so far, we've only seen one side of the sun. And now we are starting to see the whole beast.
We know that these active regions can create solar eruptions, and these solar eruptions can then create solar weather events on Earth when they disrupt the magnetosphere, and it can affect satellites, it can affect power grids and telecommunication networks. Do you expect Solar Orbiter can help us understand space weather better, or even prevent these disruptions in the future?
I don't think we will be able to prevent them. The sun is just much too powerful for that. But what we hope at some point is to be able to make predictions. For that, the first thing that is missing is a proper understanding of what causes these eruptions. How does the change of the magnetic field? We know that the magnetic field is causing it, but we don't know how the magnetic field has to develop and change to lead up to such an eruption. And Solar Orbiter, by providing us a very different view than is possible from Earth, will definitely be a big help to reach this understanding.
Thank you. Chris, Solar Orbiter's instruments were designed to essentially work together, the remote sensing cameras, the telescopes with the in-situ instruments on the spacecraft, to unlock the mysteries like the coronal heating, like space weather. What exactly can in-situ instrument teams, such as the Solar Wind Analyzer team, learn from the images that we have seen today, and how these images help you interpret your data? What questions will you be able to answer?
Yeah, well, that's right. So most of the big headline goals, the novel parts of the mission rely on us all working together and being able to link the measurements or the images of the dynamics on the sun with what is coming out past the spacecraft. So to do that, or in that sense, these images are one end of the system that will provide us knowledge about the specific sources of the solar wind that we measure at the spacecraft, and provide the kind of diagnostics that you're seeing here on the screen in this information leaflet. Just shows how, for example, the SPICE instrument is able to focus in on a candidate source region and return diagnostics about the temperature. Sami talked about how his instrument will produce information about the magnetic field. We can get information about the outflows, and in particular here we can see the graphs that shows the relative composition of the plasma in those source regions, and so that's a key part for making the link out and understanding the dynamics and the physics of what's going on in the atmosphere.
So you will see the differences between the different regions. Do I understand it correctly?
Yeah, that's right. So so different parts, whether it's a coronal hole or an active region, will have a different signature in all of these phenomena, and we see fast solar wind and slow solar wind coming out past the spacecraft that's detected by the in-situ instruments. And as I say, the key to making the science leaps are about making those links between the two sets of measurements.
I also understand that the Solar Wind Analyzer made some really unique measurements during this first close approach to the sun. Can you tell us a little bit about that?
Yeah, so actually, so that also relates to what I just said and the plot that was at the lower end. So this is a good example of the link. I mean, in particular, one of the sensors in our instrument is going to make the first dedicated measurements of the heavy ions component in the solar wind. So most of the solar wind is made up of protons and helium particles and electrons to balance the charge, but it contains these rather exotic heavy particles at different charge states. So the carbon, the oxygen, the iron, etc. And our instrument is making the first measurements of these. What you see on the screen here is in the blobs are representative of each particle that enters the instrument, and we categorize it by what's its energy, its charge, and its mass. And so we can get a kind of a fingerprint of the composition of the the solar wind passing the spacecraft, which is a direct comparison to the SPICE measurements that were in the last plot. And that enables us to establish what that link is, and then we can bring the full power of the full set of 10 instruments to the problem and understand some of the key issues like the coronal heating problem or the acceleration of the solar wind.
Thank you. Danielle, we have seen so far images from 2 of the 6 remote sensing instruments. We couldn't invite everybody, unfortunately, to talk in this press conference. From your perspective, what were the other highlights of this first imaging campaign? What other interesting things did you learn?
One real highlight for me, Teresa, was getting the grand perspective of the sun and heliosphere for the first time. We have these 2 coronagraphs on board. One is called METIS, which images the corona around the sun at the distance of several solar radii. And then we have the heliospheric imager called SOLO-HI, which looks sideways over the edge of our heat shield and images the wider space around the sun. So that impressed me really a lot to see those first images, even though they are still rough around the edges, because the night we launched, it struck me that Solar Orbiter would go and explore faraway parts of the solar system. And like Sami was saying earlier, see the sun from a completely different perspective. And when I first combined the first light image of SOLO-HI with images of the sun itself, it was really as if the spacecraft had sent us a postcard from its journey.
That's great. Holly, are there any opportunities for the cooperation between Solar Orbiter and the Parker Solar Probe?
Absolutely. And in fact, before we even launched, we were working with that team to make sure that we were planning to take advantage of the different conjunctions of the 2 spacecraft. For instance, Parker Solar Probe, when it's very close to the sun, and Solar Orbiter can image the context, the environment around it. And that provides a lot of information about what Parker Solar Probe is sampling. And some other instruments on Parker are also the same instruments or measuring the same thing on Solar Orbiter. And so there are other conjunctions where we can measure something at Parker and measure it also at Solar Orbiter, and again, link the 2 and see how that plasma has evolved, if at all. So it's very exciting. It's a very good synergy between the 2 missions.
Thank you. Jose, we mentioned that the Solar Orbiter is not yet in its full science phase. Could you just explain briefly the difference between these various phases?
Well, yes. Now that the commissioning has finished, we are doing our first steps in the so-called cruise phase. The cruise phase will bring Solar Orbiter into the final science mission. During the cruise phase, the in-situ instruments will be performing science, and the remote sensing instruments will be performing also science during dedicated remote sensing checkout windows.
Can you explain why does it take so long for the spacecraft to get to the required orbit?
Well, yes. I mean, given the mass of the spacecraft and the performance of the launcher, the initial orbit where the rocket injects Solar Orbiter has to be changed in order to end up in the final science orbit. Well, orbits in space can be changed either performing maneuvers, which would imply consuming huge amount of propellant, or performing planetary flybys. And we have opted for the planetary flybys. And Solar Orbiter is doing a tour of planets, doing, as Daniel said before, slingshots or gravity assist maneuvers around Venus and Earth in order to arrive to the science orbit.
Thank you. Danielle, what is next for Solar Orbiter?
Well, as you have explained earlier, we have now embarked on what we call the cruise phase. I should really say that for the in-situ instruments that measure the solar wind, the magnetic field, and the heliosphere, it's already full-on science. So Chris will surely talk about that later as well. In addition to that, we will be using these planetary flybys twice at Venus and once at Earth to tweak our orbit over the next year and a half. We'll also use different, let's say, thermal configurations when we are far away from the sun or closer to the sun to check how the telescopes perform when they are warmer or cooler in temperature on board the spacecraft. And this, I'm sure this 1.5 years will really fly by in no time. And then in November 2021, we'll do a last swing by at Earth at an altitude of just 440 kilometers, so really close to home. We should be able to see it with small telescopes. And then we are on our way. And then in March 2022, we will have the first really close flyby when we are roughly at 30% of the distance between Sun and Earth. So that is fantastic. And then over the next few years, while we are in this 5 to 6 month orbit, where we have very high resolution images every couple of months, we will gradually incline our orbit to see the polar regions for the first time. So that will be the last, let's say, change of perspective, and it's definitely worth waiting for, because we really believe this will give us a lot of new insight into the sun's activity cycle. So what ultimately drives these 11-year periodic changes in the magnetic field activity of the sun.
So when do we expect the next scientific results, the next images?
Well, the next images will probably be taken at the next, let's say, intermediate perihelion, roughly short, a little below 0.5 AU. So it's a little closer than the images we've seen now. We'll see that during the cruise phase. And then in March 2022, we'll get into the full-blown science phase with unprecedented resolution. So this will be the main milestone to look out for.
Thank you. Chris, can you tell us what's next for the in-situ instruments?
Well, yes, as Daniel said, in fact, those of us that are associated with an in-situ instrument are lucky enough to benefit from the fact that there's enough telemetry bandwidth for us to be turned on and operating pretty much continuously through the cruise phase and the entire mission. So the cruise phase already started on June the 15th. So we are, the 4 instruments in the in-situ group are returning data as we speak, and we will be using that to gather long-term data sets on the nature of the solar wind. There are lots of interesting physical things, fundamental physical things from an plasma and astrophysical point of view that go on in the solar wind itself, and a big community of scientists will be eagerly looking forward to that data to study things like turbulence and shocks and the various plasma instabilities, and as well also to address some of the sort of the space weather aspects of how the sun affects the Earth. So we will be detecting coronal mass ejections and solar energetic particles, etc. So
I know that there are also, we have mentioned the Parker Solar Probe, but I understand there are also some interesting opportunities to work together with Bepi-Colombo, which is another ESA mission that is now heading towards.
Yes, for sure. So I mean, Holly,
can you tell us a little bit about these cooperation opportunities?
Yeah, so Holly talked about Parker Solar Probe, and we are certainly looking at the horizon for those alignments where we will make sure we take the best measurements we can. But later on in the middle of next year, there's a very close meeting of Bepi-Colombo and Solar Orbiter. So we'll be able to make dual point measurements of, say, CMEs. There's some limitations about only having measurements at one point. So almost every opportunity that we can grab to make multi-point measurements when these spacecraft get into a useful alignment, we'll be taking that over the next 18 months before we start to get into the full science phase. So lots of science to do in the meantime.
I just explained, you said CMAs, so maybe some of our viewers don't understand. It's coronal mass ejections. And they spread from the sun, and you can measure them at various points as they sort of like evolve.
That's right. We see them coming out from the sun in the images, and we detect them in interplanetary space. And when they hit the Earth system, they can cause quite a lot of disruption as well. So it's kind of important space weather phenomena to understand better, and we'll certainly contribute to that.
And I understand that's quite unique to have this network of spacecraft measuring it like this. Is that correct?
Certainly, I mean, it's a fantastic fleet to have now for the inner heliosphere. I mean, I guess we've always looked for these kind of opportunities, but yes, it's a kind of a rich time at the moment for this kind of science.
Thank you. Sami, David, the images from EOI and FE that we have seen today were taken from almost twice the distance than Solar Orbiter is meant to operate once in its science phase. So I have 2 questions for both of you. How much better will the images get, and what are you looking forward to see? So I wonder, David, do you want to go first?
Yes. So obviously, like you say, if we fly twice closer, our images will get twice sharper. But it's going to be much better than that, I believe. You have to remember that the current data that we are showing today are merely byproducts of technical tests that we were doing. These images are not optimized yet, or the instruments are not fully configured yet. While we improve on that, I expect also that will improve the images by at least a factor 2 in contrast, in sharpness, in all sorts of ways. And so and also at the spacecraft level, by the way, steering a spacecraft is a complicated business, and so also there our optimizations are ongoing that will improve the image quality. Now, what I'm looking forward to is we have presented today perhaps the first evidence of what Daniel explained, the nanoflare theory with the campfires, but there are competing theories out there based on waves traveling through the solar corona, and we know that with the present instruments we should be able to observe them. So I'm much looking forward to also collect evidence for the competing theories and then evaluate which theory is the most prominent one or the most correct one, perhaps, in which circumstances, and that's going to be very exciting, I believe.
Sami, from your perspective?
Yes. So indeed, I think I can echo David's words. Our instrument as well is not yet in the state where we hope it will be in 1.5 years' time when we get into the science phase. And so the data that we are seeing now, although optically we can already say that the instrument is really far better than we had dared to hope, but still the data will improve, and then they will get better again because it will have much higher resolution by being closer to the sun. But the thing I'm really looking forward to is the phase when solar orbiter goes out of the ecliptic and looks down at the poles. The poles are terra incognita. It's like, the Earth 150 years ago. Nobody had been at the poles. So there will be a lot of new things to learn there. And one of the things which excites me the most is we know that the magnetic field is responsible for all the activity that the sun produces, but we don't know how the magnetic field itself is produced. We think it's a dynamo that is doing that inside the sun, a little bit similar to a dynamo inside the Earth, which produces the Earth's magnetic field. But we really don't know how it functions. But we do know that the poles play a key role in that. However, we don't have the data. And that is where Solar Orbiter will also revolutionize things.
It's fantastic. So let's have a look at some of the questions that we have received from the journalists. I have a question here from Lisa Grossman from Science News. When will Solar Orbiter take its first pictures of the sun's poles? So I guess, Daniel, would you like to take this answer, or Jose?
Well, I can do that, Teresa. We will, as we explained earlier, be gradually leaving the ecliptic plane. So it'll be, let's say, not one fixed date, but I can give you a date to work with, and that is in 2025. We will be at an angle where it starts getting interesting. And then in the beginning of 2027, we'll reach an angle from which I think especially Sami will be just delighted to get all this data. So roughly about 5 years from now, this is when the polar sign starts coming, and it will be fantastic, I'm sure.
Thank you. Our next question is from a journalist called Thorsten Dambeck from a German newspaper, and he asks, when can we expect more solar activity so that the Solar Orbiter could even see more exciting things going on at the sun compared to the quiet phase happening now? So I assume, Sami, would you like to take this question?
Yes, I can try. A little bit the problem is that we cannot really predict when activity picks up on the sun. However, we have expectations, and the expectation is that it should start to pick up. We see already the first active regions of the new solar cycle, and at the moment it's still a trickle, but at some point we think it's going to become a real river of them flowing through. And so we hope by the time we get close to the sun and into the real science phase, we will have a much more active sun.
There's another question from Thorsten, and that says, when will the first combined observation with the Parker Solar Probe mission take place? So maybe, Holly, would you like to answer this one?
Sure. I mean, Parker has already been taking data since it's been launched, and so as soon as we get the science data, we are just early in the stages for Solar Orbiter. But I'm sure the scientists will be working together as soon as possible to really see when that data can be combined. And so we will have certain campaigns, but I know that the scientists, some scientists are on both teams, are already working hard to see how that data can be combined.
Okay, I'm not seeing any further questions being forwarded from my colleagues, so I'll give them a little bit of time. And now just something arrived, so apologies for that. So we have a question from See Your Space Journey, which is a US podcast, and the journalist is Chuck Fields. Hello, Chuck. And the first question he has is, what is the approximate size of each of the campfires in today's images? When Solar Orbiter makes its closest approach to the sun at 42 million kilometers, how much smaller campfire features will it be able to resolve in size compared to the images released today? So I think, David, would you like to take this question?
Yeah, sure. The campfires that we see today are the smallest ones are a couple of our pixels. A pixel corresponds to 400 kilometers, the spatial resolution. So it's about the size of a European country, say. That's the size of the smallest campfires. The thing with the solar corona is that it's scale invariant. So if you look at smaller scales, you see smaller stuff. So I'm expecting that as we go closer, make our images better, get high resolution, that we will see yet smaller ones.
There is one more question from Chuck. And he asks, of the various imagers on board Solar Orbiter, can you define what the highest resolution in terms of pixels for the images released today? What is the highest resolution in terms of pixels for the images released today of the imagers on board Solar Orbiter? I don't know who would like to take this. Maybe Daniel?
Well, I think David raised his hand already, so I'll let David take that. Yeah.
So the movies that you saw in which we showed the campfires, the high resolution EOV images, they are really pixel limited. So the resolution of a telescope is defined as twice the pixels. So the smallest features that we see in those images, the smallest campfires, are indeed 2 pixels.
Mm-hmm. Next question is from PA Media, from Nilima Marshall. And she asks, how long does it take for the scientists to see the images taken by the instruments on the Solar Orbiter from the moment they are taken? Is it almost instantaneous, or does it take a few days? Daniel, would you like to take this one, or someone else?
Sure, I can give it a try, and Jose Luis can correct me.
Or Jose Luis, yeah.
If there are further details. So right now, in what we call the cruise phase, we have 3 antenna passes per week. So roughly every second day, we spend about 8 to 9 hours downlinking the data from the spacecraft to a big antenna of our ESA S-Track network. So that defines roughly the turnaround time. That the closer you are to one of these downlink passes, the sooner you get the data. For the nominal mission phase, we will have roughly 1 pass a day. So that means roughly within a day, the instrument teams have the data.
So maybe, Jose Luis, could you perhaps kind of compare like how operating a deep space mission like Solar Orbiter differs from, let's say, if you have a spacecraft in Earth's orbit and some other sun-observing missions?
Well, I think that there are 2 very important factors. One is the distance to the spacecraft. So we have to deal with one-way light time, which is the time that the signal that leaves the antenna takes to arrive to the spacecraft. For example, just today we are around 11 minutes. So when we send a command to the spacecraft, it takes 11 minutes to arrive to the spacecraft, and then 11 minutes to come back the telemetry. This is one aspect. The other aspect, also related to distance, is what Daniel was mentioning also before, is the bandwidth. When you are away, the bandwidth is reducing. When you are close to the Earth, the bandwidth is increasing. So the Solar Orbiter orbit is elliptic. Sometimes is closer to the Earth, sometimes is farther away. So depending on that, we are adapting the so-called telemetry bitrate, which is the bandwidth at which we can downlink data from the instruments.
Thank you. I think Sami wanted to add something to this question. Sami, do you still want to add something?
Yes, yeah. So I think it's even more complex than that. And the reason is that these images that we are taking, instruments like UI and Phi, but also the other remote sensing instruments, they're quite big. That's a lot of data. And most solar missions are close to Earth because the sun gives us many photons, lots of data, and we can get them down easily. Solar Orbiter is a deep space mission. And so telemetry is really a major limiting factor. That's why even during the nominal mission phase, the remote sensing instruments per orbit will only have 3 10-day windows in which we can take images. And then we typically have to wait weeks to months till we get those images down.
Thank you. Next question is from Business Insider, from Dave Mosher. And he asks, in the first image that was zoomed in on, there seems to be an oval-shaped dust bunny. What is that object? Is it a defect or perhaps caused by the solar environment? I think probably for David would be this one, right?
Right. We often joke that is our exobiology experiment with a little tardigrade or an insect crawling over our images. But in fact, it's a sensor defect. It's in our flat field. And so in future processing, when we further optimize this will be cleaned up and interpolated from nearby pixels. But for the moment, it's still clearly visible. And the reason why it's crawling is that the original images were actually a bit shaky. And so in software, we have corrected that shakiness and they're rock solid now. But when you do that, then the things that were fixed, like defects in the detector, they start jumping up and down. And so you see this flat field part now, the tardigrade, as we call it, or the gummy bear, moving across the image.
Next question is from the Telegraph, from the UK, from Sarah Knapton. And she asks, might there be a link between campfires and space weather? Who would like to answer this one? David again or Daniel? Hello?
Well, yeah. I can give it a try. That's an interesting question. And this is a question where the answer will crucially depend on the measurements from the Phi instrument. And this is why we put a lot of emphasis in these joint observations from more than one instrument, because what really counts is whether the region that we are looking at will be magnetically connected to interplanetary space. So to be relevant for space weather, the magnetic field must not close down on the solar surface at all times, but really open up into space and eventually reach Earth. So from these first images that the Phi instrument has been taken close to that period, it looked as if all these features really are local features that don't make it into the solar wind. But there might be situations where this is different. And that is really an interesting question to consider, whether in this case with a joint operation of, let's say, EUI, the Phi instrument, and then the in situ instrument at the location of the spacecraft, like the magnetometer, we might be able to identify a link and thereby really nail down, let's say, the driving mechanism that caused space weather.
Does anybody want to add anything to this? No. So, or yes? No. So next question I have from Franco Mecconi from Latam Satellitao. And he is asking, what is the total expected duration of the mission? That is, for how long can we expect Solar Orbiter to work? So I think either Daniel or Jose would like to answer that.
Yeah. Okay, so the total duration of the mission that it has been designed for is over 10 years. And of course, there are a number of factors that limit the lifetime of a mission. One is fuel, and the other one is solar array performance. So on the fuel side, we are good. We got a picture-perfect launch thanks to our American partners, so from the United Launch Alliance, under contract with NASA. So the launch that put us into our initial trajectory was so good that no maneuver was needed to correct it. And that really saved us a significant amount of fuel that we can then use for extending the mission. And the other part is the power returned by the solar arrays. Solar arrays in space can degrade by being exposed to intense particle showers, like protons, for example, and that depend on solar activity. So it's hard to predict, but also there, we will be, let's say, looking forward to harnessing any extra lifetime we could get. I mean, typically engineers are conservative when they design these pieces of hardware. So if they guarantee that it will last for 10 years, there's a good chance it will last longer.
Thank you. Next question is from Monica Young from Sky and Telescope, and it's for David Bergmans. What region specifically do EUI images reach in the solar atmosphere? That is, what is the technical name? Transition region, chromosphere?
Okay, so we in fact, EUI has 3 telescopes. The high-resolution images that you saw today with the campfires, these are taken in the extreme ultraviolet at 17 nanometers, and they correspond to 1 million degree in what we call the solar corona. Then there is the full sun imager, which takes the almost, let's say, full sky images with the big elephant in the picture. This has 2 wavelengths, the same wavelength as before, so the coronal images, but also a transition region image, which we typically color red. This is at 13.4 nanometer. And then there is a third telescope, high-resolution Lyman Alpha telescope, which takes images in the, not in the extreme ultraviolet, but let's say the regular ultraviolet, at the Lyman Alpha wavelength, which is at 121 nanometers. And this region, it's a bit complicated, but it combines the chromosphere and the transition region.
Thank you. So next question is from Industry and Technology. It's a French, I apologize for my pronunciation. And the question is, I would like you to explain, if possible, the main technical principle of the instruments that allow the space probe to take images of the sun. Furthermore, what type of spectroscopy did it use to take images at visible wavelengths? Who would like to answer this question?
So Sami here, I can say something about the visible wavelengths. So the PHI instrument observes in the visible. We make use of the Zeeman effect, the splitting and polarimetry of spectral lines to measure the magnetic field. It's an imager, but it's a narrowband imager, which looks at different wavelengths within a spectral line and just around it at close wavelengths to that. And the filter graph that does that is a so-called Fabry-Perot instrument, using a novel technology which has never flown in space before, using lithium niobate etalons. This is now very technical, but I understood that the question is quite technical.
Thank you, Sami. Next question we have is from Cosmos Magazine, Richard Lovett. Apologize if I pronounce it incorrectly. And he asks, how much energy do these small flares, the campfires, produce? Who would like to take this one? David, maybe, or Daniel?
I can take it, yeah. The short answer is we don't know. So at the moment, we're just taking the first images. We see something is going on there. In our images, they are very bright and very dynamic, which means there is lots of energy in there. But to accurately determine what the temperature and what the energy content is of the events, we must have instruments collaborate. An instrument like EUI will not tell you that. You need a spectrograph like SPICE. And so we're much looking forward now in the next phases to combine data from different instruments. And it's only then that we will be able to answer that indeed critical question.
Thank you. Do we have any other questions? I have to, now it's coming. I apologize for the delay. So we have a question from Irish TV from Leo Enright. How might the particles and fields instruments be used to understand the campfires? So I think maybe Chris, would you like to take this one since it asks about the in-situ instruments?
Well, I guess this is a mini version of the whole reason we're doing this mission is that we want to understand how all of these features that we might detect in the corona of the sun and the physics that's behind them, how they affect the solar wind. So for sure, I mean, Daniel mentioned their effect on interplanetary space depends on whether they're magnetically connected to the spacecraft or not. But there might be regions where they are on magnetic fields and have free access out into space. So in principle, these could be very important if there are enough of them that they can drive the bulk of the solar wind, or they between them they make up the bulk of the solar wind. Then that's really important for interplanetary space and understanding how the solar wind and therefore the sun affects our own local space environment. But answering these kind of questions is, I think, what Solar Orbiter is really all about.
Thank you, Chris. Let's wait whether we'll get any further questions in, and if we don't, I have one question for each of you before we. Now it's come. So it's Josh Warren from BCFM Radio Bristol. Given the proximity to the sun, how does the orbiter protect itself from the sun? What does it need to protect itself against the sun? Is it excess heat? What does it need to protect itself against? Is it excess heat? Is it the solar wind? What are the dangers that the orbiter might face? So I think that might be for Jose or for Daniel, who would like to take this question.
Well, I can say that the Solar Orbiter has a heat shield in front of it, and the spacecraft is, let's say, hiding behind this shield, this heat shield. And another feature of the spacecraft is that we are facing with this heat shield always to the sun, and the heat shields have doors that we open in order to allow the remote sensing instruments to observe through. And this is the biggest protection of the spacecraft in this very harsh environment. The solar rays, as soon as we get closer to the sun, we tilt them, we count them such that we offer less space to the sun, and they don't get very hot. And these are the main protections.
I think Daniel would like to add something to this. So Daniel, if you want to add anything.
Yes, I think in addition to what José Luis just correctly explained, it's also important to note that behind these heat shield doors, we still have, let's say, instruments that are sensitive, so they all have their individual tricks up their sleeves to deal with the intense heat. So, for example, the Phi instrument has a very sophisticated multi-layer coating that reflects almost the entire spectrum of light, except for the small part that the instrument can use for its observations. And then we have the SPICE instrument that has another trick. It's effectively letting all the instrument pass through the backside of the spacecraft, and it's just filtering out with a grating a particular piece in the ultraviolet that it is using. And our X-ray instrument has even a metallic shield made out of beryllium, which is unpenetrable for normal light, but the X-rays get through. So there are, let's say, custom-made solutions for each instrument to keep it safe.
And I also understand that the solar panels had to be designed to tilt so that they are not like full-on exposed to the sunlight. There are many, many interesting things. You won't probably be able to address all of them. I think Chris also would like to add something to this.
I was just going to add to, I mean, the question kind of asked about the variety of engineering challenges that we might have had to face. I would just going to point out that one of the things that I find sort of somewhat fascinating, we have 3 sensors, 2 of which are on the front of the spacecraft and have cutouts in the heat shield so they can view in the solar direction. And the third one is on the end of the boom, which sits in the shadow. So the first 2 have very clever solutions to have their own heat shields and let the thermal energy pass straight through them and out the back of the instrument. The third one, we actually have to deploy quite powerful heaters on in order to keep it warm enough, because it never sees the sun, and so it only sees the very cold of deep space. So paradoxically, on a spacecraft that is going close to the sun, we are heating our instrument.
Thank you. We still have a little bit of time left, so I have one last question for everybody, and that is, what is your favorite solar mystery that you hope Solar Orbiter will solve? And I was thinking maybe Holly could start.
Sure. I mean, that's really difficult to choose one, but I think I'm most excited about really learning more from the polar regions and how the sun generates the magnetic field, because I think that's going to be really, really useful for space weather prediction and forecasting.
Thank you. Could perhaps Sami go next? What's your favorite mystery?
Actually, very much the same. I'm also looking forward to seeing how the magnetic field is produced and learning about that, and also how everything hangs together in the solar atmosphere and out into the heliosphere. So I'm really looking forward to work together with David and Frederic, the PI of SPICE, and others, to solve what these campfires are, what is causing coronal heating, etc. So I think there's so many exciting things coming up.
Thank you, David. Would you like to go next?
Yeah, I think I can echo what Sami says. Perhaps what I'm really looking forward is, of all these crazy little things that we are seeing in the high resolution images, which are the ones that actually matter for the heliosphere? Which one of those do make it outside there? Because most of it is falling back and is just of local importance in the corona, but some of it must be creating the solar wind or must be relevant for it.
Thank you. Chris, what is your favorite mystery? What are you really looking forward to solve?
Yes, I completely endorse. I mean, these are all the big questions that we've spent the last 10 years or more building this mission to address. So absolutely, those are things that we're looking forward to. I might be a bit more parochial and say, well, as a representative of the in situ group, we've added some what I think are interesting bells and whistles working together. So, for example, we're going to try to work out on board between us when a shockwave passes a spacecraft and use that to capture some very short periods of high resolution. It's not part of the main goals, perhaps, but it'll be fun to see how that works. And if it does, I think we'll end up with some great new data concerning collisionless shocks. So for the community that's into that kind of thing, stay tuned. I hope that's something that will be fun and interesting.
Fantastic. Daniel, what about you?
I think I can really only add to what has been said before. I think I'm let's say, really torn between the big picture, the ultimate goal of really having the entire team of 10 instruments perform together and connect the dots. I think that to me is really the overarching goal of the mission. But then in addition, because I have to admit, I'm also not very patient. And right now, having seen these first fantastic images from EOI, I'm just excited in the short term to look into those in more detail and use the power of our UV spectrometer and the magnetograph to shed more light of those.
Thank you, Daniel. Last is Jose. So I'm just wondering, because Jose is more involved in the operations kind of side of things. So what are you in general looking forward to in terms of the Solar Orbiter mission, which I can understand is quite interesting in terms of its trajectory and the operations?
Well, I'm really looking forward to arrive to the nominal science orbit and how we operate around perihelion with the very harsh environment and the huge amount of data to be downlinked. And this is going to be challenging because we will receive also from the scientists very last minute requests that we have to insert in our timeline, and this will be really part of our work in ESA.
Thank you, Jose. I think we will have to wrap up right now. So for more information about Solar Orbiter, go to esa.int/solarorbiter. If you want to arrange interviews with our panelists or other ESA and related experts, please email media@esa.int. Thank you, everybody, for joining us today, and we will look forward to sharing more Solar Orbiter breakthroughs with you in the future.